What makes interpreting Earth observation satellite data so difficult? Imagine trying to piece together a giant puzzle where each piece looks different and comes from a different box. That's what analyzing Earth observation satellite data feels like. These satellites orbit hundreds of kilometers above the planet, collecting a vast array of information. But turning that raw data into useful insights is a real challenge. First, these satellites use many types of sensors: optical cameras, radar systems, thermal sensors, and hyperspectral devices. Each sensor captures data in different ways. Optical sensors work like regular cameras, taking pictures in visible light. Radar sensors send out radio waves and measure how they bounce back, even through clouds. Thermal sensors detect heat emitted from the Earth's surface. Because each sensor type has its own resolution, data format, and way of capturing information, combining all these sources takes a lot of work. For example, optical images might have a resolution of less than 1 meter, while radar images could be several meters. Making these different data types work together requires complex calibration and processing. Next, the data itself comes in many formats, such as GeoDF, NetCDF, or HDF5, and uses different coordinate systems. Handling these large files, which can be gigabytes or even terabytes in size, demands powerful computers and sophisticated software. Processing steps include correcting geometric distortions caused by the satellite's movement, removing sensor errors, and adjusting for atmospheric effects like clouds, haze, or dust. Without proper processing, the data can be misleading or unusable. Quality issues also make interpretation tricky. Clouds can obscure land features, and atmospheric particles can change the spectral signatures that sensors detect. If these aren't corrected, the data might suggest false changes or hide real ones. For example, a cloud-covered area might look like it has no vegetation, even if it does. Ensuring data reliability involves multiple correction steps, which are time-consuming and requiring expertise. Aligning data over time is another challenge. Satellites follow different orbits, so images taken days or weeks apart might not line up perfectly. Small shifts can lead to errors when analyzing changes in land use or vegetation health. To compare images accurately, scientists must perform precise registration, which can be complex when dealing with different satellites and sensors. Developing models to interpret the data adds another layer of difficulty. Radiative transfer models simulate how light interacts with the atmosphere and surface, but they are computationally intensive. They need detailed input data, like atmospheric conditions and surface properties, which are often hard to obtain. Creating algorithms that quickly and accurately extract meaningful information from raw signals remains a significant task. Validation is also essential. To trust satellite data, scientists compare their results with ground truth measurements collected on site. Gathering this reference data over large or remote areas is costly and logistically difficult. Without it, the accuracy of satellite-derived products can be uncertain, limiting their usefulness. Finally, combining physics-based models with machine learning approaches offers promise but requires large, high-quality datasets and expertise in both fields. Training these models takes time and resources, and errors in training data can lead to misleading results. All these factors, sensor diversity, data complexity, quality issues, alignment challenges, modeling difficulties, and validation needs, make interpreting Earth observation satellite data a complex task. Yet, overcoming these hurdles is vital for applications like monitoring climate change, managing natural resources, or responding to disasters. It's the combination of advanced satellite technology and dedicated scientists working behind the scenes that makes it possible to turn raw satellite signals into meaningful stories about our planet.